My name is Bekbauova A. Today I would like to present our research entitled Stability of a Periodic Solution in the Broad Sense of Evolutionary Systems. This work is devoted to the study of periodic solutions of evolutionary systems and the investigation of conditions under which these solutions remain stable over time. Evolutionary systems play an important role in describing a wide variety of physical and technical processes. They arise in wave propagation, oscillation theory, electrical current dynamics, and automatic control systems. Because of their broad range of applications, the study of existence and the stability of solutions for such systems remains an important problem in modern mathematics. Numerous classical and contemporary studies provide the theoretical foundation for this research. The theory of nonlinear oscillations in the periodic solutions has been developed by many outstanding mathematicians. Among them are Henry Poincare, Alexander Lyapunov, Nikolai Krylov, Nikolai Bogolyubov, Yuri Mitropolsky, and Anatoly Samoylenko. Their works established fundamental methods for the analysis of nonlinear differential equations and the periodic processes. Our research continues this line of investigation by studying periodic solutions of evolutionary systems and their stability properties. Let us consider a system of first-order partial differential equations. The system contains two unknown vector functions denoted by u and v. These equations describe the evolution of the system with respect to time and the spatial variables. The initial conditions determine the state of the system at the initial moment. Our objective is to investigate the existence of periodic solutions and analyze their stability. In this model, the coefficient functions and the matrices are assumed to be bounded and periodic with respect to certain variables. The matrices B sub ij are diagonal matrices. Several norms are introduced to estimate the behavior of solutions. These norms allow us to formulate rigorous conditions for stability in the convergence. First, we introduce the concept of periodicity. A function is called periodic in the variables t and x if its values repeat after a specified period. In other words, shifting the variables by the corresponding period leaves the function unchanged. This definition serves as a foundation for the entire analysis. Next, we define a solution in the broad sense, also called a generalized solution. Such a solution is continuous, periodic, and satisfies the system along characteristic curves. This concept is important because classical solutions do not always exist. The generalized approach makes it possible to study a broader class of evolutionary systems. To construct the fundamental solution, we first consider the corresponding homogeneous system. In this case, the external forcing terms are equal to 0. The analysis of the homogeneous system reveals the intrinsic dynamics of the model and provides the basis for further results. This slide presents an important lemma. We assume that the coefficients of the system are continuous, bounded, and satisfies the Lipschitz condition. Under the assumptions, the system possesses favorable mathematical properties. In particular, they guarantee the existence and uniqueness of solutions. Using the previous assumptions, we derive an integral matrix equation. The matrices U and V describe the evolution of solutions along characteristic trajectories. These matrices play a central role in constructing the fundamental solution of the system. The lemma shows that the integral equation possesses a unique continuous bounded solution. Moreover, this solution can be represented as a uniformly convergent series. This result forms the theoretical basis for the subsequent stability analysis. Here we introduce the concepts of fundamental matrices and the normalized fundamental matrices. These matrices satisfy the homogeneous system and reduce to the identity matrix at the initial moment. They serve as the principal analytical tool for studying the behavior of solutions. This slide presents important estimates for the fundamental matrices. The obtained inequalities demonstrate exponential decay over time. Consequently, the corresponding solutions also exhibit exponential stability properties. These estimates are essential for proving the main stability results. We now introduce the concept of asymptotic stability. A solution is called asymptotically stable if it approaches zero at time tends to infinity. This means that sufficiently small perturbations gradually vanish and the system returns to its equilibrium state. The study of this property is one of the central objectives of our work. Next, we extend the analysis to a nonlinear system of first-order partial differential equations. The presence of nonlinear terms makes the model more realistic, but also significantly more challenging to analyze. Therefore, additional mathematical techniques are required. The nonlinear functions are assumed to be periodic and satisfy Lipschitz conditions. These assumptions impose bounds on the growth of the nonlinear terms. As a result, the corresponding solution can be extended throughout the entire domain under consideration. This slide introduces the definition of a periodic solution in the broad sense for the nonlinear system. Such a solution is bounded, periodic, and continuously differentiable along characteristic curves. This definition extends the concept previously introduced for the linear case. So, Theorem 1 is one of the principal results of this work. It states that under the assumptions of the lemma and the specified conditions, the nonlinear hyperbolic system possesses a unique periodic solution in the broad sense. Thus, both existence and uniqueness are established. To prove Theorem 1, we construct a special operator Q. We show that this operator maps a suitable space into itself and is a construction. Then, by the construction mapping principle, the operator has a unique fixed point. This fixed point corresponds to the described periodic solution in the broad sense. So, Theorem 2 concerns a stability of the periodic solution. It states that the periodic solution obtained in Theorem 1 is uniformly asymptotically stable. In other words, solutions that begin sufficiently close to the periodic solution remain close and eventually converge to it. To establish stability, we introduce a transformation that shifts the periodic solution to the origin. This enables us to study the stability of the zero solution instead. The transformed system preserves the essential properties of the original nonlinear system. Next, we derive estimates for the transformed solution. These inequalities describes the evolution of the solution over time. The estimates involve both the fundamental matrices and the nonlinear terms. They provide the basis for determining the asymptotic behavior of solutions. Finally, we apply the Bellman-Gronwall lemma inequality. This yields an explicit estimate for the solution. The resulting bound shows that the solution converges to zero as time tends to infinity. Therefore, the periodic solution is uniformly asymptotically stable. This completes the proof. So, to conclude, we investigated periodic solutions of evolutionary systems in the broad sense. We established sufficient conditions for their existence, uniqueness, and asymptotic stability. The obtained results contribute to the theory of nonlinear evolutionary systems and may be useful in applications related to physical and engineering processes. Thank you for your attention.